Hello, everyone, and thank you for joining this webinar. I'm Nilofar Shirani, an assistant research professor at Connecticut Transportation Institute at the University of Connecticut, and I served as the principal investigator of this project. This project was completed by our research team at the University of Connecticut, including Oluwaseun Olufawabi, a graduate research assistant in the Department of Civil and Environmental Engineering, and Noah Rudermill, a research assistant too at the Connecticut Transportation Institute. Today, I'm pleased to present our completed research project titled Evaluating Older Drivers' Reaction to Forward Collision Warning and Automated Emergency Braking under Conditions of Distraction using a Driving Simulator. This project was carried out over almost 2 years and consisted of 2 completed phases. The first phase focused on building the foundation for the study. During this stage, we reviewed the existing literature, developed the experimental protocol, obtained institutional review board approval, drafting pre- and post-drive surveys, and designed the driving simulator scenarios to evaluate 3 ADAS configurations. The second phase focused on the experimental work. We recruited older adult drivers, conducted the simulator experiments, analyzed the data, interpreted the findings, and prepared the final report with recommendations for future research and ADAS design. Together, these 2 phases allowed us to comprehensively evaluate how cognitive distraction influences older drivers when interacting with these safety technologies. Now let's discuss why this research is important. The world's population is aging rapidly. By 2030, approximately 1 in every 6 people worldwide will be over the age of 60. And in the United States, the number of licensed drivers aged 65 and older has increased substantially over the past 2 decades. Although many older drivers and many older adults remain safe and experienced drivers, aging naturally affects several abilities that are important for safe driving, including visual perception, attention, reaction time, and cognitive processing speed. At the same time, modern vehicles are increasingly equipped with advanced driver assistance systems such as forward collision warning and automated emergency braking. These technologies have demonstrated significant potential to reduce crashes and improve roadway safety. However, despite these advances, relatively little research has examined how these systems perform specifically for older adults, particularly when drivers are cognitively distracted. So this knowledge gap provided the motivation for our study. Based on the motivation, our study was designed to answer 3 primary questions. First, we wanted to understand how cognitive distraction influences older drivers' reaction time. Second, we wanted to determine whether different ADAS configuration influence driver performance under distraction. And finally, we wanted to evaluate how older adults perceive these technologies after using them, specifically in terms of comfort, trust, reliability, and willingness to use them. Before conducting the experiment, we hypothesized that distraction would increase reaction time and reduce the driving performance. We also expected that the combined FCW plus AEB would provide the greatest safety benefits and receive the highest user rates. To answer our research questions, we designed a controlled driving simulator experiment using a mixed method between subject design. Before recruiting participants, we first conducted a statistical power analysis to determine the minimum sample size required to detect meaningful differences while maintaining adequate statistical power. Based on This analysis, we determined that 48 participants would be sufficient for our study, and we recruited 48 licensed driver age 65 years and older. Participants were randomly assigned to one of 6 experimental groups based on 2 independent variables. The first independent variable was ADAS configurations, which included FCW, AEB, and the combined FCW plus AEB systems. The second independent variable was the driving condition, where participants either completed the experiment under cognitive distraction or without the distraction. Throughout the experiment, we collected both objective and subjective measures. Our primary objective measure was reaction time, which we defined as the time between the appearance of a hazard and the driver's initial brake response. We also evaluated braking behavior, and after completed the drive, participants rated each system in terms of comfort, reliability, trust, and usability through a post-drive questionnaire. Each participant completed approximately a 10 minutes drive in simulator. During this drive, participants encountered 2 unexpected hazards. As you can see in these figures, the first event involved a pedestrian suddenly entering the roadway from the side. The second involved a parked vehicle unexpectedly pulling into the travel lane, as you can see here. These scenarios were selected because they represent realistic situations that require drivers to react quickly in order to avoid collision. To ensure consistency, all participants experienced identical roadway geometry, traffic conditions, and environmental settings. This allowed us to isolate the effect of distraction and ADAS configuration without introducing other confounding factors. The experiment followed a structured 5-step procedure. Participants first reviewed the study information, signed the consent form, and completed a questionnaire regarding their driving history and familiarity with ADAS technologies. Next, they completed a practice drive to become familiar with the driving simulator. During the experimental drive, participants assigned to distraction condition engaged in a neutral conversation with the researcher. This created cognitive workload without introducing visual or manual distraction, making it representative of common real-world conversation while driving. Participants in the control group completed the same drive without distraction. And finally, after finishing the drive, all participants completed a post-drive questionnaire evaluating assigned ADAS technologies. After completing data collection, we had 2 different data sets. These 2 main sources of information was driving simulator data, which included objective performance measures such as reaction time, braking behavior, and the system responses recorded during each hazard event. The second was the survey data, which included participants' responses from both a pre-drive and post-drive questionnaires, such as their familiarity with ADAS technologies and their rating of comfort, reliability, trust, and willingness to use the assigned system. Before conducting any statistical analysis, we first performed descriptive statistics to summarize the characteristics of our participants and to better understand the overall distribution of both the simulator and survey data. We then selected statistical methods based on the type of data we were analyzing. The simulator data, particularly reaction time, for that we used a mixed design ANOVA to evaluate the effect of ADAS configuration, distraction condition, and hazard event, as well as the interactions among these factors. For the survey data, since the responses were collected using a Likert scales and did not necessarily satisfy the assumption required for parametric test, we used cross-call Wallis test to compare participants' rating across the different ADAS configurations and distraction conditions. Together, these analyses allowed us to evaluate both the objective driving performance and the subjective perception of older drivers when interacting with different ADAS technologies. Let's now move to the main findings from the mixed design ANOVA. As shown in the table, the strongest effect was cognitive distraction. We found a highly significant main effect of distraction on reaction time with a value of 49.37 and p-value less than 0.001. This indicates that older drivers took significantly longer to respond to hazardous events when they were cognitively distracted compared with when they were not distracted. We also found a significant main effect of ADAS configuration with an f-value of 3.86 and a p-value of 0.03. This result indicates that reaction time differed across the three ADAS configurations, although we needed post hoc analysis to determine which specific systems differed from one another. In contrast, the hazard event itself did not significantly affect reaction time with an f-value of 0.49 and p-value of 0.48. This suggests that participants responded similarly to both hazard scenarios. Looking at the interaction effects, neither the interaction between the systems and distraction, nor the interaction between system and event, nor the three-way interaction reached statistical significance. However, the interaction between distraction and event approached significance with a p-value of 0.07, suggesting a possible trend that warranted further investigation in the post-hoc analysis. Overall, these results indicate that cognitive distraction had the greatest influence on older drivers' reaction time, while the effect of ADAS configuration were smaller and there was little evidence that the type of hazard event altered driver responses. To better understand the ANOVA findings, we conducted post-hoc analysis. For the main effect of ADAS system, we observed a marginal effect with f-value of 2.72 with a p-value of 0.07, suggesting that the type of ADAS system may influence reaction time. As shown in the figure on the left, participants using combined FCW plus AEB system had the shortest average reaction time, while those using FCW only system had the longest reaction time. We also examined the interaction between distraction and event, which showed a marginal effect with f-value of 3.45 and p-value of 0.07. As shown in the figure on the right, reaction times remained relatively stable for participants without distraction, whereas distracted participants showed longer reaction time during the second hazard event, suggesting that cognitive distraction may have a greater impact over repeated driving events. In addition to evaluating driving performance, we also wanted to understand how participants perceived the different ADAS systems after completing the experiment. Participants completed a post-drive survey where they rated the science system in terms of comfort, willingness to use, and reliability. We analyzed these survey responses using the cross-call-Wallis test. As shown in the three figures, participants in the non-distraction group generally gave higher rating across all three measures compared with those in the distraction group. In particular, the combined FCW plus AEB systems received the highest rating for willingness to use and reliability among participants who drove without distraction. However, although these trends are visible in the figures, the cross-call-Wallis test did not identify any statistically significant differences among the ADAS configurations or between distraction conditions, with all p-value greater than 0.05. Overall, these findings suggest that participants tended to perceive the systems more positively when they were not cognitively distracted, even though those differences were not statistically significant. Several important conclusions emerged from this study. First, cognitive distraction significantly delayed older drivers' reaction time. Second, although the combined FCW plus AEB system generally produced faster responses and more positive user perceptions, these improvements were not statistically significant. And finally, our findings demonstrate that the effectiveness of ADAS depends not only on the technology itself, but also on the cognitive state of driver. This highlights the importance of designing systems that are predictable and capable of supporting drivers without increasing their cognitive workload. This research contributes to transportation safety research in several important ways. It provides new evidence regarding the effect of cognitive distraction on older drivers using ADAS and also helping address an important gaps in the current literature. So the finding also provide guidance for designing more age-inclusive driver assistance systems. Moving forward, future research should investigate different alert modalities, interface designs, adaptive warning strategies, and driver training approaches that can improve both safety and long-term user acceptance. This slide summarizes the major findings of this project. Among all variables, the examined cognitive distraction had the strongest influence on reaction time. The combined FCW plus AEB systems generally resulted in the fastest responses, although those differences were only marginally significant. Participants also rated the systems more positively when they completed the drive without distraction. And overall, these findings reinforce the importance of considering human factor, particularly cognitive workload, with developing future driver assistant technologies. Thank you very much for your time and attention. I would like to acknowledge the support of the New England University Transportation Center and the U.S. Department of Transportation for funding this research. I would also like to thank my research team for their valuable contribution throughout this project. Thank you again for joining today's webinar. I appreciate your interest in our work, and I hope you found this presentation informative. Have a wonderful day.